So in this example problem, we're asked to solve for the displacement at the free end of our cantilever beam, all right, using the following equations for VC of x. So we're basically, these are our shape functions, VC of x, all right. So we've already completed step 1 of Rayleigh's method, all right, which is done. So step 2 asks us, we need to determine our u and our w. Okay, so the first step is we need to define VC of x. Our second step is to define u and w. And our third step is to set u equal to w and solve for our unknown. Alright, so in this case, the unknown is going to be delta. So in each of these three examples, we're looking to solve for delta. Alright, so for part A, we're assuming VC of x is equal to minus delta 1 minus cosine of pi x over 2L. So first thing we need to do is we need to determine our distributed load, our work done due to our concentrated force. So work for a concentrated force is just going to be equal to 1/2 times the force, which in this case we're going to write as negative P because it's going along the negative y-axis, times the displacement at that point here. So this is the displacement at x is equal to L. So we're going to just plug in x is equal to L from our load. So if we do that, we get minus delta times 1 minus cosine pi of L over 2L. Alright, so the L's will cancel out. Pi over 2 is equal to 0. And then we end up with just a 1/2 times minus P times negative delta. Alright, so that's going to be equal to 1/2 P delta for our work done. Alright, and then for the second part of the problem, it asks us to find, the second part of step 2 is we need to determine what u is. So u is going to be equal to 1/2 the integral of 0 to L e to the iz, alright, times the VC, the second derivative of VC of x squared dx. Okay, so we need to figure out what VC, the second derivative of VC of x with respect to x is. So we'll first take v prime of x, alright, so v prime of x, well, let me first rewrite VC of x. VC of x is equal to negative pi 1 minus cosine pi L over 2L. Or 2, sorry, pi x times cosine over 2L. Alright, so if we take the derivative of that with respect to x, alright, we're going to get minus delta times 0 minus the derivative of cosine is negative sine, so we'll get a positive sine of pi x over 2L, and then we have to take multiply that by the derivative of the inside term of the sine function, which would just be, in this case, would be pi over 2L. Okay, so so if we rearrange this, we get minus delta over sine of pi x over 2L. Minus negative sine of pi x over 2L times pi over 2L. Alright, so then we can then take the derivative of this term of v prime c of x with respect to x. Again, if we do that, we would end up getting negative delta as a constant, pi over 2L as a constant, and then the derivative of sine is just cosine of pi x over 2L, and then we have to take the derivative of the inside term due to the chain rule. So if we do that, we would get pi over 2L again. So if we multiply all this through, we get negative delta pi squared over 4L squared cosine pi x over 2L. Okay, so what we're going to now do is we're going to plug this term into our original integral and solve for u. So we get u is going to be equal to 1/2 the integral from 0 to L e to the I z times negative delta pi squared 4L squared cosine pi x over 2L squared dx. Okay, so what we end up getting here is we get u is going to be equal to 1/2 times e to the I z we can take out. Alright, all these terms, this coefficient out front here is all a constant, so we can take out this term here. So this is going to end up being delta squared pi to the 4th over 16 L to the 4th. Alright, and then we're going to be left with the integral from 0 to L of cosine squared of pi x over 2L dx. Alright, so in order to evaluate this, the integral of cosine squared, we can go back to the integration tables. So if we go back to the integration tables, if you go to integration formula number 68, there's an integral for the cosine squared a of x d of x in your lecture packet, and that's going to be equal to x over 2 plus sine of 2ax over 4a. Okay, so in our case, a is equal to pi over 2L. Okay, so alright, and so what we'll end up getting here is we get u is going to be equal to 1 over 2 e to the I z delta squared pi over 4 times 6 divided by 16 L to the 4th times x over 2 plus sine of 2ax over 4a. Okay, so that is, and you have to evaluate that from L to 0. Okay, so if we plug in our values of a here, a is equal to pi over, our a's will actually cancel out in this, well, no, sorry, they will not cancel out. So let's plug in let's plug in our value for a here. So if we do that, we'll get 1/2 this coefficient here times x over 2 plus sine of pi x over L divided by 4 or divided by 2 pi over L. And we evaluate that from L to 0. Alright, so if we plug that all in, we'll get 1/2 times our big coefficient here times x over 2, which will just be L over 2, plus the sine of pi, which is just equal to 0 over 2 pi L. And then for when x is equal to 0, the sine of 0 is 0, and x over 0 over 2 is also 0. Okay, so we just get this L over 2 term is the only thing that we need to worry about. If we multiply the L over 2 term times all this, we end up getting 1 over 2 times 16 is 32. 2 times 2 is again 64. L cubed over e to the I z delta squared pi to the 4th. Alright, and that'll be our strain energy. Alright, so the last part of the problem is that we need to do is we have our u term and we have our work term. So what we can then do is we can set, so our work term is just 1/2 pi delta, our our strain energy term is equal to 1 over 64 times all this stuff. So then what we're going to do, our last step is we're going to set U equal to W and solve for delta. All right, so U would be 1 over 64 e to the IZ delta squared pi to the fourth over L cubed. All right, this is equal to 1/2 the applied force times delta. Okay, so if we rearrange this and solve for delta, we'll keep delta on the left-hand side, and we're going to get 32 PL cubed over pi to the fourth times e to the IZ. If we evaluate 32 over pi to the fourth, what that ends up being is 0.329 PL cubed over e to the IZ. All right. So if we look at using Castigliano's method and traditional beam theory, so if you look at like the back of your textbook and you look for the displacement as a function, if you look for delta at the end of the beam is going to be equal to, so it's going to be equal to 0.333 or 1/3 times PL cubed over e to the IZ. All right, so the difference between these two is about 3% different. Okay, so it's pretty good solution relatively, considering we just took an educated guess on what we thought the shape of the beam would be as a function of x based off the boundary condition. So this kind of shows you how you could assume a shape of a structure, and using Rayleigh's method, you can still get a pretty close result to what you need. All right. So I'm going to stop this example problem here, but there are two additional problems that you could solve, or two additional constants that you could, or shape functions that you could assume, and you can see how close those would be to the original shape. Okay. All right. And one of the nice things I guess I should mention here too is that once you get delta, right, you then know the displacement at any point along the structure. So using Rayleigh's method, you can solve for the displacement at any point once you determine your unknown constant.